Physics usually treats the universe like a sealed box. Everything that exists is inside it. Energy can move around, matter can change form, but nothing enters and nothing leaves. The rules assume the system is closed, but that assumption has started to look a little less certain. Over the last few decades, physicists have built models where our universe is only one region inside a much larger structure. In these ideas, space does not stop at the edge of our cosmos. Other regions could exist nearby, with their own physics, their own histories, maybe even their own versions of space and time. At first, this sounded like pure speculation, a mathematical possibility, nothing more. Then scientists began noticing small puzzles. Certain patterns in the oldest light in the universe look slightly uneven. Some physical constants appear strangely fine-tuned. And in a few theoretical models, forces we measure here could actually be influenced by dimensions or regions we cannot see. None of this proves another universe is out there, but it raises a strange question. What if our universe isn't completely isolated? If reality is more like a thin boundary than a solid wall, something outside it could occasionally affect what happens inside. Not through dramatic openings or portals, but through subtle changes in energy, gravity, or the structure of space itself. In other words, if another reality existed close enough, the first sign might not be obvious at all. It might look like tiny cracks in the rules of our own universe. You've been told the universe is expanding at a constant rate. The data reveals that's wrong. Dead wrong. New measurements from the James Webb Telescope suggest something far more unsettling. The expansion isn't constant. It's accelerating. Faster and faster. But here's the controversial part. Our current models can't explain it. The math doesn't work. Dark energy. Dark matter. It's not enough. The evidence shows a deeper problem. Something is fundamentally altering the fabric of space-time itself. Is another reality leaking into ours? The implications extend far beyond astrophysics. 7%. That's the margin by which our universe's expansion rate defies the standard cosmological model. 7% might not sound like much, but in cosmological terms, it's a chasm, a gaping hole in our understanding of, well, everything. It's a discrepancy that's been nagging at physicists for years, growing louder with each new measurement. And now James Webb is screaming it from the rooftops. It's called the Hubble tension. And it's not just a minor statistical anomaly, it's a fundamental disagreement between how fast the universe should be expanding based on its early conditions and how fast it actually is expanding as measured today. Let's examine the players here. On one side, we have the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. By studying the CMB, we can calculate the Hubble constant, the rate at which the universe is expanding, with incredible precision. On the other side, we have direct measurements of the expansion rate using objects like Cepheid variable stars and Type 1a supernovae. These standard candles allow us to measure distances to galaxies and, consequently, their recession velocities. The problem? The Hubble constant derived from the CMB is significantly lower than the one measured using these standard candles. It's like trying to bake a cake using two different recipes that call for drastically different amounts of flour. Something isn't adding up. Now, for a long time, some hoped this tension would simply evaporate with better data. Maybe there were systematic errors in our measurements. Maybe we were misinterpreting the light from these distant objects. But Webb's observations are making that explanation increasingly difficult to swallow. Webb's infrared vision allows it to see through the dust that obscures many distant Cepheid variables, providing much more precise distance measurements than ever before. And what Webb is finding is that the discrepancy isn't going away. In fact, it might even be getting worse. This leaves us with two possibilities, neither of them particularly comforting. First, maybe our understanding of the early universe is incomplete. Perhaps there's some exotic physics at play in the first few moments after the Big Bang that we're simply not accounting for. This could involve new particles, new forces, or even modifications to general relativity itself. Second, maybe our understanding of the late-time universe is flawed. Maybe there's something fundamentally wrong with how we're measuring distances to galaxies. Or, more disturbingly, maybe the universe isn't as homogeneous as we thought it was. Maybe there are vast, unseen structures that are affecting the expansion rate in different regions of space. Consider this. If The universe isn't uniform. If there are pockets where dark energy is stronger or where the density of matter is higher, then our measurements of the Hubble constant could be skewed. We might be getting a false reading because we're only seeing a small, biased sample of the cosmos. The implications extend far beyond just a disagreement over a number. If the Hubble constant is truly different in different parts of the universe, it would challenge our most basic assumptions about cosmology. It would suggest that the universe is far more complex and mysterious than we ever imagined. And here's what's wild. Some physicists are starting to entertain an even more radical idea. What if the accelerating expansion isn't driven by dark energy at all? What if it's being influenced by something else entirely, something that lies beyond the realm of our observable universe? Could it be that another universe with its own physical laws and constants is subtly interacting with ours, tugging on the fabric of spacetime and causing it to expand at an ever-increasing rate? It sounds like science fiction, but the data reveals that we can't rule it out. The idea isn't that another universe is physically colliding with ours. Instead, the concept involves subtle gravitational interactions, or perhaps even the exchange of hypothetical particles that can pass between universes. These interactions, though weak, could be enough to influence the expansion rate of our universe, especially on the larger scales. The evidence shows that the current models are inadequate. They simply cannot account for the accelerating expansion without invoking some form of exotic dark energy, and even then, the numbers don't quite add up. So, the possibility of external influence, however far-fetched it may seem, remains on the table. Scientists discovered that some areas of the universe appear to be expanding faster than others. This challenges the fundamental principle of homogeneity, which assumes that the universe is uniform on large scales. If the universe is not homogeneous, it opens the door to the possibility that other universes with different properties could be influencing our own. This means we need to rethink everything, from the nature of dark energy to the validity of the cosmological principle. The cracks in the cosmic mirror are widening, and they may be reflecting something far stranger than we ever anticipated. What if what we perceive as empty space isn't so empty after all? What if it's a gateway, a conduit to realities beyond our comprehension? Ever wonder why some astronomical structures seem impossible? Like they shouldn't exist, given what we know about the universe? We're talking about things that defy the standard models. Galaxies that are too big, too old, or too organized for their supposed age. Black holes that are too massive. Cosmic voids that are too empty. These anomalies might just be whispers from somewhere else. Consider the Boötes void. It's a staggeringly large region of space, nearly 330 million light-years across, with hardly any galaxies. Our models predict voids, sure, but nothing on this scale. It's so empty, it's almost unnatural. Some scientists have jokingly referred to it as the Great Nothing. The probability of finding a void that large, that empty within the standard cosmological model is vanishingly small. So what created it? What keeps it so empty? One intriguing, albeit speculative, hypothesis suggests that the Boötes void might be the result of the merger of multiple smaller voids. However, even that explanation struggles to account for its sheer size and emptiness. Could it be that the void is being actively maintained by something? An unseen force, or perhaps an influence from outside our universe? It's a long shot, definitely. But the sheer improbability of the void forces us to consider unconventional possibilities. Then there are the supermassive black holes. We know they exist at the centers of most galaxies, including our own Milky Way. But some of these behemoths are simply too big. They shouldn't have had enough time to grow to their current size, given the age of the universe. The standard accretion models, which describe how black holes accumulate mass by swallowing surrounding matter, struggle to explain their rapid growth. How did they get so massive so quickly? One possibility is that they formed from direct collapse black holes, which are hypothetical objects that could have formed directly from the gravitational collapse of massive gas clouds in the early universe, bypassing the need for gradual accretion. Another idea is that they merged with other black holes, growing in leaps and bounds. But even these scenarios have limitations. Perhaps, just perhaps, these supermassive black holes are tapping into a source of energy or matter that we don't yet understand. A connection, however tenuous, to another reality where the rules of physics might be different. It sounds far-fetched, I know, but the sheer scale of these objects and the difficulty in explaining their formation within our current framework opens the door to speculation. And it's not just the size of these objects, it's their spin. Some supermassive black holes are spinning at nearly the maximum theoretical limit, meaning they're whirling around incredibly fast. This rapid spin can influence the space-time around them, creating a region known as the ergosphere where objects can extract energy from the black hole. The question is, how did they get spinning so fast? The standard models suggest that black holes acquire their spin through accretion, as they gradually consume matter that is rotating around them. But to reach such extreme spin rates, they would need to accrete matter in a highly ordered way, without any significant counter-rotating material that could slow them down. This requires very specific conditions, which may not be common in the universe. Is it possible that the spin of these black holes is being influenced by something external, a force or interaction that we haven't yet detected? It's a question that's worth exploring, especially if we want to truly understand the nature of these enigmatic objects. Let's examine the large quasar groups, LQGs. These are some of the largest known structures in the observable universe, consisting of dozens of quasars clustered together over vast distances. Their size is so immense that they challenge the cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales. Homogeneous means the same everywhere, and isotropic means the same in every direction. These LQGs can span billions of light years, making them some of the most extreme structures we've ever observed. Their existence suggests that the universe may not be as uniform as we once thought, and that there may be regions where matter is clustered together in unusual ways. The formation of these LQGs is still a mystery. The standard models struggle to explain how such large structures could have formed in the time since the Big Bang. Gravity alone may not be enough to pull these quasars together over such vast distances. Could it be that these LQGs are being influenced by something beyond our universe? An external force or field that is shaping the distribution of matter on the larger scales? It's a speculative idea, but one that's worth considering if we want to understand the true nature of the cosmos. It's like the universe is trying to tell us something, but we don't quite understand the language it's speaking. These structures, these anomalies, could be the key to unlocking a deeper understanding of reality. Consider this for a moment. What if the very laws of physics aren't as constant as we believe? What if they vary slightly from one region of the universe to another, or even from one universe to another? This could explain some of the anomalies we're seeing, as well as the accelerating expansion of the universe. The idea that the laws of physics might not be universal is a radical one, but it's not entirely without precedent. Some theories, such as string theory and the multiverse hypothesis, suggest that our universe is just one of many, each with its own set of physical laws and constants. If these other universes exist, they could be subtly influencing our own, causing variations in the laws of physics. These variations could be incredibly small, but they could have significant effects on the large-scale structure of the universe. They could affect the formation of galaxies, the growth of black holes, and the expansion rate of the cosmos. They could even explain why some areas of the universe appear to be expanding faster than others. Ultimately, the existence of these impossible structures and unseen forces may be pointing to something even more profound, that our universe is not an isolated entity, but rather an interconnected part of a larger, more complex reality. The implications extend far beyond astrophysics. It would force us to rethink our understanding of the fundamental laws of nature, the origin of the universe, and our place in the cosmos. The analysis continued. What if there are forces at play that we simply cannot detect with our current technology? This kept me up last night. You know when you stumble across an idea, something so bizarre and unsettling that it just burrows into your brain? That's what happened when I started looking at the quantum foam. Okay, quick refresher. Quantum foam is this theoretical idea that at the smallest scales of the universe, space-time isn't smooth, but rather a frothing, bubbling mess of quantum fluctuations. Virtual particles popping in and out of existence, tiny wormholes flickering open and closed. It's wild stuff, and usually it's considered to be confined to the Planck scale. Mind-bogglingly small. But what if it's not? What if, under certain circumstances, those quantum fluctuations could somehow scale up? What if they could leave a detectable imprint on the larger universe? The idea sounds insane, I know, but bear with me. Think about it this way. We're detecting these anomalies, these impossible structures, these unseen forces. We're struggling to explain them with our current understanding of physics. What if these are, in a sense, echoes from the quantum foam? Faint whispers from that seething subatomic realm, amplified and imprinted onto the cosmos. It's like the universe is a giant instrument and the quantum foam is the musician, playing a melody we can barely hear, but whose notes are still shaping the music. I know what you're thinking. This sounds like pure speculation. And, to be fair, it is. But sometimes the most outlandish ideas are the ones that lead to the biggest breakthroughs. Let's examine the implications. If these anomalies are related to quantum foam, it would mean that our understanding of spacetime is fundamentally incomplete. It would mean that the boundary between the quantum world and the classical world is far more blurred than we ever imagined. It would also potentially offer a way to probe the quantum realm in a way we never thought possible. Instead of building ever more powerful particle colliders, we could simply look to the sky and read the echoes of the quantum foam imprinted on the cosmic microwave background or the distribution of galaxies. Here's what's wild. Some scientists have proposed that dark energy, that mysterious force driving the accelerating expansion of the universe, could be related to the energy of the quantum foam. If that's the case, then these anomalies could be a window into understanding the biggest mystery in cosmology. Consider the implications for the multiverse. If the quantum foam is truly a seething cauldron of possibilities, then it could be the source of new universes. Every quantum fluctuation could be a potential birth event, a tiny bubble of space-time expanding into its own reality. If this is true, then our universe is not unique. It's just one of countless others, all spawned from the same quantum foam. And these other universes might not be governed by the same laws of physics as our own. This could explain the variations we're seeing in the fundamental constants. It could explain why some regions of the universe seem to be expanding faster than others. It could even explain why the universe seems to be fine-tuned for life. Maybe we're not so special after all. Maybe we're just lucky to be in a universe that happens to be hospitable to life. But that doesn't make our universe any less precious. It just means that we need to appreciate it even more. But there's a darker side to this idea. If the quantum foam is constantly generating new universes, then it's also possible that it could destroy our own. A rogue quantum fluctuation could create a bubble of space-time with different laws of physics, which could then expand and consume our universe. It's a terrifying thought, but it's one that we need to consider. The universe is a dangerous place, and we need to be prepared for anything. December the 12th, 2012. The day a seemingly innocuous paper landed in the inbox of a theoretical physicist at Princeton. It wasn't the title, something about quantum entanglement and black hole interiors, that initially grabbed his attention. It was a single offhand comment tucked away in the appendix, a comment that, if true, threw the entire concept of space-time into question. The physicist, Dr. Leonard Susskind, had been wrestling with the black hole information paradox for years. This paradox essentially asks, what happens to information that falls into a black hole? Does it disappear forever, violating the fundamental laws of quantum mechanics? Or is it somehow preserved? Susskind and others had proposed a radical solution, the firewall paradox. This idea suggested that at the event horizon of a black hole, instead of a smooth transition, there exists a literal wall of fire, a region of extremely high-energy particles that would incinerate anything that crossed it. The firewall was a way to preserve information, but it came at a steep cost. It violated the principle of general relativity, which dictates that an observer falling into a black hole shouldn't experience anything particularly dramatic at the event horizon. They should simply pass through, unaware of crossing any boundary. Susskind hated the firewall idea. It felt like a kludge, an ugly patch on a beautiful theory. But he couldn't find a way around it. Then came that paper in his inbox. The authors, through a series of complex calculations, proposed a new interpretation of quantum entanglement, the phenomenon where two particles become linked regardless of the distance separating them. They suggested that entanglement could create microscopic wormholes, tiny tunnels connecting the entangled particles through space-time. This was a radical idea, but it offered a potential solution to the information paradox. If every particle inside a black hole was entangled with a corresponding particle outside, then these microscopic wormholes could create a pathway for information to escape. But here's where things get really strange. The paper also suggested that these wormholes weren't just limited to black holes. They could exist anywhere in space-time, connecting any two entangled particles. And if that's true, then the entire fabric of reality might be far more interconnected than we ever imagined. It could mean that distant regions of the universe are linked by a vast network of microscopic wormholes, allowing for the instantaneous transfer of information and, potentially, something else entirely. The Princeton physicist realized something profound. What if the firewall wasn't a wall of fire at all? What if it was a manifestation of these microscopic wormholes, a region where space-time itself was being stretched and distorted by the intense entanglement between the inside and outside of the black hole? The firewall, in this view, wasn't a destructive barrier, but a gateway to another region of space-time connected to our own through the quantum entanglement of particles. This reimagining of the firewall paradox has profound implications. It suggests that the boundaries between different regions of space-time might not be as rigid as we thought. It opens up the possibility that information, and perhaps even matter, can travel between these regions through the network of microscopic wormholes. Consider the implications for our understanding of dark matter. Could dark matter be ordinary matter located in another region of space-time interacting with our own through these wormhole connections? It sounds like science fiction, but the math is starting to suggest that it's possible. Furthermore, consider the implications for the arrow of time. Our universe seems to have a distinct direction of time, moving from the past to the future. But what if other regions of space-time have different arrows of time? Could these wormhole connections allow for the transfer of information or even objects from the future to the past? Again, these are highly speculative ideas, but they're based on solid theoretical physics. The firewall paradox, once seen as a problem, is now becoming a window into a deeper understanding of the universe. What would be the impact on our basic assumptions about the universe? Everyone assumed dark energy was a constant, a uniform pressure pushing the universe apart at an ever-increasing rate. But what if that's not the whole story? What if dark energy isn't some fundamental property of space-time, but rather a symptom? Consider this. We know the universe is expanding, and that this expansion is accelerating. We attribute this acceleration to dark energy, a mysterious force we don't fully understand. But what if the observed expansion isn't due to a force within our universe, but rather a pressure from without? Think of it like this. Imagine a balloon submerged in water. The water exerts pressure on the balloon, keeping it compressed. Now, imagine slowly decreasing the water pressure. The balloon will expand. Is the expansion caused by some force inside the balloon? No, it's caused by the reduction of external pressure. What if our universe is like that balloon? What if the water is another reality, another region of space-time with different properties? And what if the dark energy we observe is simply the pressure exerted by this other reality on our own? It sounds far-fetched, I know, but it elegantly explains some of the biggest mysteries in cosmology. One of them is the cosmological constant problem. The observed value of dark energy is vastly smaller than what theoretical physics predicts, like by 120 orders of magnitude smaller. It's arguably the worst prediction in the history of physics. Why is dark energy so weak? Perhaps it isn't weak. Perhaps what we're measuring isn't the intrinsic strength of dark energy, but rather the difference in pressure between our universe and another. If the other reality has a slightly higher pressure than ours, the resulting expansion would be much smaller than what we'd expect from a universe filled with dark energy at the theoretically predicted level. Furthermore, this model could explain the observed homogeneity of the universe. The cosmic microwave background, the afterglow of the Big Bang, is remarkably uniform across the entire sky. This suggests that the early universe was incredibly well mixed, with almost identical conditions everywhere. But how did this happen? The Standard Model invokes a period of rapid inflation in the early universe to explain this homogeneity. But what if the uniformity was imposed from the outside? If our universe is in contact with another reality, that reality could act as a kind of heat bath, evening out temperature differences and ensuring a uniform distribution of energy. Scientists discovered something else too. This idea also has implications for the distribution of dark matter. As we discussed, dark matter makes up about 85% of the matter in the universe, but we have no idea what it is. It doesn't interact with light, making it invisible to telescopes. But what if dark matter isn't a new type of particle at all? What if it's simply ordinary matter located in this other region of space-time, exerting a gravitational pull on our own universe? This would explain why dark matter seems to be distributed in a halo around galaxies. The gravitational influence of matter in the other reality would be strongest at the edges of our galaxies, creating the illusion of a dark matter halo. The implications extend beyond cosmology. It could even shed light on the nature of consciousness. Some physicists have suggested that consciousness might not be confined to the brain, but rather extend into the quantum realm, potentially interacting with other regions of spacetime. If this is true, then the other reality might not be just a physical space, but also a realm of consciousness. This could explain some of the more puzzling aspects of quantum mechanics, such as the observer effect, where the act of observing a quantum system seems to change its behavior. Of course, this is all highly speculative. There's no direct evidence to support the idea of another reality exerting pressure on our own. But it's a fascinating thought experiment that could potentially solve some of the biggest mysteries in physics. Measurements showed that we need to be careful about not falling into the trap of confirmation bias. It's easy to see patterns where none exist, to cherry-pick data that supports our pet theories. That's why it's crucial to subject these ideas to rigorous testing. How could we test the hypothesis that dark energy is actually interdimensional pressure? One approach would be to look for subtle variations in the expansion rate of the universe. If the pressure from the other reality isn't perfectly uniform, there might be slight differences in the expansion rate in different directions. Another approach would be to look for evidence of wormholes, microscopic tunnels connecting our universe to the other reality. These wormholes might be too small to detect directly, but they could have subtle effects on the way light travels through space. And then there's the possibility of detecting dark matter particles directly. If dark matter is indeed ordinary matter from another reality, it might be possible to detect it using highly sensitive detectors. Further examination revealed these are all long shots, I admit. But the potential payoff is enormous. If we could prove that our universe is connected to another reality, it would revolutionize our understanding of the cosmos. It would open up entirely new avenues of research and could potentially lead to breakthroughs in technology and medicine. The analysis continued. It's a long road ahead, but the journey is worth it. The quest to understand the universe is one of the most important endeavors of humankind. And who knows? Maybe, just maybe, we're on the verge of a discovery that will change everything. There's a massive problem with the Standard Model, and it's staring us right in the face. Dark matter and dark energy. We can observe their effects. We can measure their abundance, but we have absolutely no idea what they are. They make up 95% of the universe, yet our best theories can't account for them. It's a bit like trying to understand an elephant by only looking at its toenails. This glaring hole in our understanding has led some physicists to revisit a rather unconventional idea, the simulation hypothesis. Now, I know what you're thinking. This sounds like something straight out of a sci-fi movie, but bear with me because some very serious minds are considering it. The simulation hypothesis, in its simplest form, proposes that our reality is not fundamental, but rather a computer simulation run by a more advanced civilization. Think the Matrix, but on a cosmic scale. If this is true, then many of the mysteries that plague us, like dark matter and dark energy, could simply be quirks or limitations of the simulation itself. They might not be fundamental components of reality, but rather coding artifacts. Consider this. A sufficiently advanced civilization could possess the technological capability to create simulations indistinguishable from reality. If they could create multiple such simulations, then the number of simulated realities would vastly outnumber the single real reality. Therefore, statistically speaking, it's more likely that we are living in a simulation than not. Now, I know this is a big leap, but let's examine how this idea could be used to explain dark matter. One possibility is that dark matter isn't matter at all. Maybe it's a kind of computational shortcut, a way for the simulators to reduce the processing power needed to render the universe. Imagine trying to simulate the gravitational interactions of every single particle in a galaxy. That would require an enormous amount of computing power. But if the simulators could approximate these interactions using some kind of simplified algorithm, they could drastically reduce the computational burden. This simplified algorithm is what we perceive as dark matter. The same logic could apply to dark energy. The expansion of the universe is another computationally intensive process to simulate. If the simulators wanted to introduce a kind of cosmic speed limit to prevent the simulation from becoming unstable, they might introduce a term that looks like dark energy. This term would effectively push the universe apart, preventing it from collapsing in on itself. Here's what's wild. This idea gets an interesting upgrade when considered alongside the potential leakage we've been discussing. What if the simulation isn't perfect? What if there are glitches or boundaries where the underlying code becomes apparent? These glitches might manifest as anomalies that we can detect, and if another simulated reality exists with slightly different parameters, its pressure on our own could be another source of these anomalies. The implications extend to the fundamental constants of nature. The speed of light, the gravitational constant, the charge of an electron, these values seem finely tuned to allow for the existence of life. If these constants were even slightly different, stars wouldn't form, atoms wouldn't bind, and the universe would be a barren wasteland. This is often referred to as the fine-tuning problem. The simulation hypothesis offers a potential solution. If our universe is just one of many simulations, then each simulation could have slightly different values for these constants. We just happen to live in one where the constants are just right for life to emerge. It's like a vast cosmic A/B test. Scientists discovered that the simulation hypothesis is not without its critics, of course. Many physicists dismiss it as unfalsifiable, meaning that there's no way to prove or disprove it using scientific methods. Others argue that it's simply an unnecessary complication, a philosophical rabbit hole that distracts us from more fruitful lines of inquiry. However, some researchers are taking the simulation hypothesis seriously and trying to find ways to test it. One approach is to look for evidence of the underlying code, for example, patterns or symmetries that wouldn't be expected in a real universe. Another approach is to try to detect glitches in the simulation, such as violations of the laws of physics. And then there's the possibility of creating our own simulations. As our computing power increases, we may eventually be able to create simulations that are indistinguishable from reality. If we do, then we'll have effectively proven that the simulation hypothesis is possible. This means that even if we can't prove that we are living in a simulation, we'll have shown that it's at least conceivable. And that in itself would be a profound discovery. The analysis continued. Are there limits to what can be simulated? Does the act of simulating a universe necessarily create new universes? These are questions that push the boundaries of physics and philosophy, forcing us to confront the very nature of reality. Nobody saw this coming. Years of theoretical physics, seemingly confined to chalkboards and academic journals, are colliding with some very strange observations. The question isn't just whether another reality could be leaking into ours, but how such a thing might even be possible. And that brings us to the truly weird stuff, exotic matter. Consider the hypothetical. What if the bridges between realities aren't tiers in space-time, but more like meticulously constructed tunnels? Tunnels that require something different to hold them open. Something we call exotic matter. Exotic matter is, well, exotic. It's a catch-all term for any hypothetical substance that violates one or more known physical laws. The most famous example is negative mass. Imagine a substance that, instead of being attracted to gravity, is repelled by it. Push it, and it moves towards you. It sounds like science fiction, but the math actually allows for it. Why is this relevant? Because one of the biggest hurdles in theoretical physics is the Einstein-Rosen bridge, or what's popularly known as a wormhole. Wormholes, if they exist, could theoretically connect two vastly different points in space-time. The problem? They're inherently unstable. They collapse almost instantly. That's where exotic matter comes in. A sufficient quantity of negative mass energy could theoretically counteract the immense gravitational forces trying to pinch the wormhole shut. It could prop it open, creating a traversable tunnel. Now, let's be clear, we've never observed negative mass. We haven't even come close. But the search is on. Scientists are exploring various avenues, from manipulating quantum fields to searching for subtle anomalies in the cosmic microwave background radiation, all in the hopes of catching a glimpse of this elusive substance. But what if exotic matter isn't just about keeping wormholes open? What if it's a fundamental component of these interreality bridges? Imagine a scenario where our universe isn't alone but exists alongside countless others, each with its own set of physical laws. These universes might be separated by vast distances, or they might be subtly interwoven, like threads in a cosmic tapestry. But what if, in certain regions, the boundaries between these universes become thin? What if they start to overlap? This is where things get really interesting. In these overlapping regions, the laws of physics might become negotiable. Normal matter, the stuff that makes up you and me, might not be able to exist in these transitional zones. But exotic matter, with its ability to defy conventional physics, might be perfectly at home. In this model, exotic matter could act as a kind of glue, binding these realities together. It could form stable structures that allow for the exchange of energy and information between universes. It could even, theoretically, allow for the transfer of matter itself. Measurements showed that this might explain some of the anomalies we're seeing: the unexplained energy bursts, the strange particle interactions, the violations of conservation laws. All of these could be signs of exotic matter at work, bridging the gap between our reality and another. Of course, this is highly speculative. We're talking about pushing the boundaries of what we know about the universe. But the beauty of science is that it allows us to explore these possibilities, to test our assumptions, and to challenge our understanding of reality. The implications extend far beyond just understanding the nature of the universe. If we could harness exotic matter, if we could learn to manipulate it, we could potentially unlock technologies that were once considered impossible. Interstellar travel, unlimited energy, even the ability to manipulate space-time itself. These are just some of the possibilities that could arise. And then, there's the darker side. If another reality is leaking into ours, what are the potential consequences? Could this influx of exotic matter destabilize our universe? Could it lead to unforeseen and potentially catastrophic events? These are questions that we need to address, and the answers may depend on understanding the role of exotic matter in these interreality connections. Here's what's wild. The search for exotic matter isn't just about finding a new substance. It's about fundamentally changing our understanding of the universe. It's about opening up new possibilities, both for good and for ill. And it's about confronting the possibility that our reality is far more complex and interconnected than we ever imagined. The analysis continued. If the multiverse is more than just a theory, the implications ripple outwards, touching everything we thought we knew about physics. Because what good are our laws of physics if they only apply to this universe? Consider the multiverse for a second, not as science fiction, but as a serious scientific proposal. It's an idea that's been gaining traction in theoretical physics for decades, fueled by everything from quantum mechanics to string theory. The basic premise is this: our universe might not be the only one. There could be an infinite number of other universes out there, each with its own set of physical laws, constants, and even its own history. Now, some multiverse theories propose that these other universes are completely separate from ours, existing in their own bubbles with no possibility of interaction. Fine. Easy to ignore. But other models suggest that these universes might be closer than we think, that they might even be able to interact with each other, however subtly. And that's where things get interesting. How could universes interact? That's the million-dollar question. One possibility, as we were discussing, involves exotic matter. If exotic matter can exist, and if it can form stable connections between universes, it could act as a bridge, allowing energy and information to flow between them. Think of it like this. Imagine our universe is a bubble floating in a cosmic ocean. Other universes are bubbles too, some close by, some far away. Most are completely isolated, minding their own business. But occasionally, two bubbles might bump into each other. And if there's a bridge between them, a tiny filament of exotic matter, energy and information can leak from one bubble to the other. This leakage could explain some of the anomalies we're seeing. Those unexplained energy bursts. Maybe they're not coming from within our universe at all, but from another one. The strange particle interactions? Perhaps they're being influenced by forces or particles that don't even exist in our reality. The violations of conservation laws? Maybe those laws are only valid within our universe, and they're being violated by the influx of energy or matter from elsewhere. Of course, this is all highly speculative. We're talking about the bleeding edge of theoretical physics here. There's no direct evidence of the multiverse, and there's no guarantee that it even exists. But the possibility is tantalizing, and the anomalies we're seeing are giving us hints that something strange is going on. And it's not just about exotic matter. Other multiverse models propose different mechanisms for interaction. Some suggest that universes can collide with each other, creating ripples in space-time that we might be able to detect. Others propose that universes can split and merge like branches on a cosmic tree. Still others suggest that our universe might be a simulation and that the real universe exists outside of our simulated reality. The point is, there are many different ways that universes could interact, and we're only just beginning to explore the possibilities. And if any of these models are correct, it could have profound implications for our understanding of the universe. Let's examine how this could affect established physics. If our universe is just one of many, and if the laws of physics vary from universe to universe, then our laws of physics might not be as fundamental as we thought. They might just be local rules that apply to our particular corner of the multiverse. The constants of nature, like the speed of light or the gravitational constant, might also vary from universe to universe. That means that our entire framework for understanding the universe might be incomplete. We might be missing crucial pieces of the puzzle because we're only seeing a tiny slice of reality. It's like trying to understand the ocean by only looking at a single drop of water. And it's not just about understanding the universe, it's also about our place in it. If the multiverse is real, then our universe might not be as special as we thought. We might just be one of an infinite number of universes, each with its own unique set of conditions. This could have a profound impact on our sense of self and our place in the cosmos. It could challenge our assumptions about the nature of reality and the meaning of existence. It could force us to confront the possibility that we're not as important or as unique as we thought we were. But it could also be incredibly liberating. If there are an infinite number of universes out there, then there are also an infinite number of possibilities. Anything that can happen will happen, somewhere in the multiverse. That means that there's an infinite number of universes where you're rich, famous, and successful. And there's also an infinite number of universes where you're a talking dog. The possibilities are endless. You've been told that physics is settled. It's not even close. And the possibility of interdimensional leakage throws a massive wrench into everything we think we know. What happens if stuff actually starts leaking through? It's not just a fun thought experiment. The consequences could be, well, let's just say, significant. Consider the most immediate and obvious impact. Our laws of physics might start to bend, or even break. We rely on these laws to predict everything, from the trajectory of a rocket to the behavior of subatomic particles. If these laws are suddenly subject to outside interference, all bets are off. Our technology, our infrastructure, our very understanding of the world around us could become unreliable overnight. Imagine bridges collapsing because gravity momentarily weakens. Picture electronic devices going haywire because the electromagnetic force fluctuates. Think about chemical reactions producing unexpected results, leading to industrial accidents or environmental disasters. That's the dramatic scenario, but there are subtler, potentially more insidious consequences to consider as well. What if the constants of nature themselves begin to shift? The speed of light, the gravitational constant, Planck's constant, these are the bedrock upon which our entire scientific framework is built. If they start to drift, even slightly, the implications would be profound. The universe as we know it might begin to unravel. Stars could burn hotter or cooler, altering the delicate balance that allows life to exist on Earth. The fundamental forces that hold atoms together could weaken or strengthen, changing the properties of matter itself. The very fabric of spacetime could warp and distort, leading to unpredictable gravitational anomalies. This wouldn't necessarily be an instantaneous catastrophe. It could be a gradual process unfolding over years, decades, or even centuries. But the cumulative effect would be devastating. Our universe would become unstable, unpredictable, and ultimately uninhabitable. Beyond the purely physical consequences, there are also the potential biological impacts to consider. If life exists in other universes, it's likely to be very different from life as we know it. Different building blocks, different genetic codes, different environmental conditions. If organisms from another universe were to cross over into ours, they could introduce new diseases, new parasites, and new forms of competition that our ecosystems are simply not equipped to handle. Our immune systems might not recognize these alien pathogens, leaving us vulnerable to devastating pandemics. Our native species might be outcompeted by more aggressive or better adapted organisms from another universe, leading to ecological collapse. And it's not just about the direct impact of alien organisms. The introduction of even a small amount of foreign matter could have unforeseen consequences for our environment. Imagine if a new element with properties unlike anything we've ever encountered were to be introduced into our atmosphere or our oceans. It could disrupt chemical cycles, alter weather patterns, and trigger a cascade of ecological effects that we can't even begin to predict. Think about the invasive species we already deal with. Now imagine those species came from a completely different universe, with entirely different evolutionary pressures. Then there's the psychological impact. How would humanity react to the knowledge that our universe is not unique, that there are other realities out there, and that those realities are potentially leaking into ours? For some, it might be a source of wonder and excitement, a chance to explore new worlds, to learn new things, to expand our understanding of the universe. But for others, it could be a source of fear and anxiety. The idea that our reality is not fixed, that it can be altered by forces beyond our control, could be deeply unsettling. Mass hysteria, social unrest, and even religious extremism could become widespread. People might lose faith in science, in government, and in each other. Conspiracy theories could flourish, fueled by misinformation and paranoia. Society could fracture along ideological lines as different groups struggle to make sense of a reality that no longer seems stable or predictable. And let's not forget the potential for exploitation. If we were able to understand and control the process of interdimensional leakage, what would we do with that knowledge? Would we use it to benefit all of humanity, or would we succumb to the temptation of power and greed? Imagine the military applications. Weapons that can manipulate the laws of physics, that can teleport objects across vast distances, or that can even open portals to other universes. The potential for destruction is almost unimaginable. Or consider the economic implications. Access to new resources, new technologies, and new markets in other universes could create unimaginable wealth. But it could also exacerbate existing inequalities, leading to even greater disparities between the rich and the poor. The point is, the consequences of interdimensional leakage are not just scientific or technological. They are also social, political, economic, and psychological. They would affect every aspect of our lives, and they would challenge our very definition of what it means to be human. Further examination revealed a disturbing possibility. What if these leaks aren't random? What if something is deliberately causing them? And then there's the truly terrifying question. What if something is already here? The idea of shielding of reality might sound like science fiction. But if even a fraction of what we've discussed is true, it's a question we need to seriously consider. Let's examine what that could even look like. I mean, how do you shield an entire reality? It's not like putting up a force field around the Earth. This is about manipulating the very fabric of space-time, potentially on a cosmic scale. One theoretical approach involves understanding and controlling the properties of dark matter and dark energy. These mysterious substances make up the vast majority of the universe, and their influence on space-time is undeniable. If we could learn to manipulate them, we might be able to tune the universe, so to speak, making it less susceptible to interdimensional leakage. It's a long shot, I know, but it's one avenue of research that some theoretical physicists are exploring. Another possibility lies in harnessing the power of quantum entanglement, this bizarre phenomenon where two particles become linked regardless of the distance separating them could potentially be used to create a sort of quantum firewall. Imagine creating a network of entangled particles that spans vast regions of space. If a dimensional breach were to occur, the entangled particles could instantly react, creating a localized distortion in spacetime that would effectively seal the leak. Now, I know what you're thinking. This sounds like something straight out of a comic book. And you're not entirely wrong. The technological hurdles involved are immense, perhaps insurmountable. But the underlying physics is sound, at least in theory, and the potential rewards are so great that it's worth exploring these ideas, however far-fetched they may seem. Consider the energy requirements alone. Manipulating dark matter, controlling quantum entanglement on a cosmic scale, these would require energy levels that dwarf anything we can currently imagine. We're talking about harnessing the power of stars, or even entire galaxies. It's almost incomprehensible. Then there's the ethical dimension. Even if we could develop the technology to shield our reality, should we? What right do we have to interfere with the natural processes of the universe? What if our attempts to fix things actually make them worse? It's a question that weighs heavily on many scientists working in this field. What if, in trying to shield ourselves, we inadvertently create even larger, more unstable dimensional breaches? Or, perhaps worse, what if we inadvertently trap something here that we can't control? The potential for unintended consequences is enormous. We also have to consider the possibility that some level of interdimensional interaction is not only inevitable, but perhaps even beneficial. Maybe these leaks are a natural part of the universe's evolution, a way for different realities to exchange information and energy. Maybe by trying to shield ourselves, we're actually cutting ourselves off from something vital, something that could help us evolve and grow as a species. Perhaps a more realistic approach is not to try to completely block these leaks, but rather to learn to understand and manage them. To develop technologies that can detect and analyze these breaches, to predict where and when they're likely to occur, and to mitigate their potential impact. This would be a more pragmatic, less ambitious goal, but it might also be more achievable. This could involve developing sophisticated sensor networks that can monitor subtle fluctuations in spacetime, changes in fundamental constants, or the appearance of exotic particles that don't belong in our reality. It could also involve creating advanced computer simulations that can model the behavior of these leaks, allowing us to predict their trajectory and potential impact. And then there's the possibility of developing countermeasures, technologies that can neutralize or redirect these breaches, preventing them from causing widespread disruption. This might involve creating localized gravitational fields that can bend spacetime, or developing energy weapons that can disrupt the flow of energy through the breach. Of course, all of this raises even more questions. Who gets to decide what constitutes a dangerous leak? Who gets to control these technologies? And how do we ensure that they're not used for malicious purposes? The ethical and political challenges are just as daunting as the scientific ones. It's a complicated situation, to say the least. The science is speculative, the technology is decades, maybe centuries away, and the ethical implications are profound. But the potential consequences of inaction are too great to ignore. If these leaks are real, and if they're becoming more frequent, we need to start thinking about how we're going to deal with them. Not just as scientists, but as a society. Perhaps the first step is simply to raise awareness, to educate the public about the potential risks and opportunities associated with interdimensional leakage, to encourage open and honest discussion about the ethical and political implications, to foster a sense of global cooperation, so that we can work together to address this challenge, regardless of our individual backgrounds or beliefs. This isn't some Hollywood movie plot. This requires serious consideration, serious research, and serious discussion. It requires the best minds on the planet working together to understand the nature of reality and our place within it. Because at the end of the day, our survival may depend on it. But what if the threat isn't external? What if the source of these leaks lies within us? 22%. That's the percentage of the universe that we think is made of dark matter, a substance we can't directly see, interact with, or fully understand. But what if dark matter isn't just some exotic particle floating in space? What if it's something else entirely? Consider this. Our current cosmological models, built on the standard model of particle physics and general relativity, are incredibly successful at explaining a vast range of phenomena. From the cosmic microwave background to the large-scale structure of the universe, they've passed test after test. Except, they also require us to invent entire categories of matter and energy that we can't directly detect. Dark matter, dark energy, these are placeholders, really. Elegant placeholders, perhaps, but placeholders nonetheless. What if these leaks we've been discussing are not breaches from some other dimension, but rather manifestations of our incomplete understanding of dark matter and dark energy? What if these mysterious substances aren't so mysterious after all, but are simply behaving in ways our current models can't predict? Maybe the problem isn't that another reality is bleeding into ours. Maybe the problem is that our reality is far more complex and far stranger than we ever imagined. Maybe dark matter isn't some passive background substance. Maybe it's dynamic, interactive, capable of forming structures and exhibiting behaviors that mimic or even influence the leaks we're observing. Think about it. We know dark matter interacts gravitationally. It's how we infer its existence in the first place. But what if it also interacts in other ways, through forces we haven't yet discovered? What if these interactions can create localized distortions in spacetime or fluctuations in the energy field that manifest as these apparent breaches? The implications for cosmology are profound. If the source of these leaks is internal, if it's tied to the nature of dark matter and dark energy, then we need to fundamentally rethink our approach to understanding the universe. We can't just focus on external factors, on searching for exotic particles or higher dimensions. We need to look inward, to the very fabric of space-time itself. This requires a new kind of cosmology, one that goes beyond the known, one that embraces the unknown, the uncertain, the potentially paradigm-shattering. It demands a willingness to challenge our most fundamental assumptions, to question the very foundations upon which our models are built. Let's examine the possibilities. Perhaps dark matter isn't a single type of particle, but a whole zoo of different particles, each with its own unique properties and interactions. Some might interact weakly with ordinary matter, while others might interact strongly with each other, forming complex structures and exhibiting collective behaviors. Or perhaps dark energy isn't a constant force, but a dynamic field that evolves over time, its strength and properties changing as the universe expands. This could lead to localized variations in the expansion rate, creating regions of space-time that are stretched or compressed, potentially giving rise to these leaks. These ideas aren't just wild speculation, they're grounded in the latest research in theoretical physics and cosmology. Scientists are exploring a wide range of alternative models for dark matter and dark energy, models that go beyond the standard paradigm and attempt to explain the anomalies and inconsistencies we're seeing in the data. And then there's the possibility that our understanding of gravity itself is incomplete. General relativity is an incredibly successful theory, but it's not without its limitations. It breaks down at extremely small scales, and it struggles to explain the accelerated expansion of the universe. Perhaps there are modifications to general relativity that can account for these phenomena, modifications that introduce new forces or interactions that mimic the effects of dark matter and dark energy. These modified gravity theories are still in their early stages of development, but they offer a promising avenue for exploring the unknown. The analysis continued. Scientists are also exploring the possibility that the universe isn't as homogeneous as we thought. Our standard cosmological models assume that the universe is roughly the same in all directions, at least on large scales. But what if there are significant variations in the density and distribution of matter, variations that can create localized distortions in spacetime? These variations could be caused by primordial black holes, formed in the early universe, or by large-scale structures that haven't yet been fully accounted for in our models. They could also be caused by topological defects, exotic objects that can arise in certain theoretical frameworks, such as string theory. This means that the future of cosmology lies in embracing complexity, in moving beyond the simple, elegant models that have served us so well in the past. It requires a willingness to explore alternative theories, to challenge our assumptions, and to embrace the unknown. It also requires a new generation of telescopes and detectors capable of probing the universe at unprecedented depths and resolutions. We need to build instruments that can directly detect dark matter or measure the properties of dark energy with greater precision. We need to search for primordial black holes and to map the large-scale structure of the universe with greater accuracy. And perhaps most importantly, we need to foster a culture of collaboration and open communication where scientists from different disciplines can come together to share their ideas and insights. The problem of interdimensional leakage, or whatever it may be, is too complex for any one individual or group to solve. It requires a collective effort, a global collaboration of the best minds on the planet. Ultimately, the search for the source of these leaks and the quest to understand the nature of dark matter and dark energy is a journey into the unknown. It's a journey that will challenge our understanding of the universe and our place within it, but it's also a journey that holds the potential to unlock some of the deepest secrets of reality. Here's what's wild. This goes beyond just understanding the cosmos. It touches on fundamental questions about the nature of reality, the limits of human knowledge, and the potential for our own consciousness to shape the universe around us. If these leaks are indeed tied to the fabric of space-time, then understanding them might give us insights into the very nature of existence itself. And that's a future worth striving for, a future of cosmology that pushes the boundaries of what's possible. So, where does all this leave us? Are we ready for first contact? How ready are we really for first contact? Not with some far-off civilization detected via radio waves, but with Something else? If reality itself is proving permeable, what safeguards do we have in place? Consider this. We barely understand the universe we think we know. What if these leaks aren't just a cosmological curiosity, but a sign that the universe is far more interconnected and fragile than we ever imagined? Perhaps these other realities are just as unprepared for us. If that's the case, let me know what you think in the comments.